Okay, your next theorem is going to include something called the included angle. So an included angle is an angle that's in the middle of two sides that are, sorry, two adjacent sides. So sides that are right by each other. So you can see here that AB is adjacent to BC. They're right beside each other. So angle B is their included angle. It's the one in the middle of those two sides. So our next theorem to prove two triangles congruent is called side angle side. That's when you have two corresponding sides that are congruent and the angle in between them are congruent. So notice on this triangle, we see that AC is congruent to DE, that EF is congruent to AB, and that angle A is congruent to angle E. This is side angle side, or SAS congruence. So if we saw two triangles like this, we could prove them congruent. I'm going to start by looking at what is given to me in the picture. So I see one hash mark here and one here. So I can say that XC is congruent to ZV. I see two hash marks here and two here. So I can say WZ is congruent to ZY. Finally, what I care about is this angle that's in between the two sides, the included angle. Side, angle, side, angles in the middle. So I want to be able to prove that Z is congruent to Z. Really, it's WZV is congruent to XZY, so it's not the same angle. They're different in the picture. You know what? I'm going to rewrite that so I don't confuse you on why I'm not using reflective. So this is angle WZV and angle YZX. Those two angles are across from each other. See? So they are vertical angles, which are always congruent. Everyone loves to forget this one. You learned it in middle school, but it's the first one that's going to slip from your mind in these proofs. But when they're across from each other, they are vertical angles. So since I have two sides and the angle in between those two sides is congruent, then you can use SAS to prove that those two triangles are all congruent.